All right. Section 2.2, power functions with modeling. What is a power function? And what makes it different from what we were talking about yesterday? So yesterday and the day before, we talked about polynomials, right? And I said for a polynomial, your exponents must be positive integers or zero, right? Well, a power function is technically any function whose exponent is not a positive integer. So we're talking about radicals and negative exponents. They make power functions. Alrighty, so we got a lot of vocabulary to talk about, and then we'll talk about the images that they make, and then we'll just do our 3 quick examples. Alrighty, so A would be considered the power, obviously. Now K, the number in front, would be a constant of variation. I hope you notice that we don't have any pluses or minuses here. It's going to be one term, a constant of variation that sits in front, and then an exponent. And that exponent could be positive, could be negative, could be all kinds of stuff. We say that f of x varies as the 8th power of x. Or we could say that f of x is proportional. I'll be saying varies. Specifically, varies directly and varies inversely. That's what we're going to be working on. Now, there are 4 possible shapes, if you were going to graph these things, that it could take on. And that's for x's that are positive. And the reason why they're positive is because we don't raise negative numbers to powers. If you try to raise a negative number to a power, you end up, instead of smooth curves, you end up with just dots. It's not possible to plot that and connect those dots. And that the reason why is because they're just full of discontinuities. You can't take the 1/2 power, which is a square root, of a negative number. But you could take the 1/3 power. Not the 1/4 power, but you could take the 1/5 power. And you see, so you end up with all of these infinite places where it's not even going to exist. So therefore, we restrict ourselves to the positive x-axis. So every one of these graphs does contain the point 1 comma k, and that's because it wouldn't matter what a is. 1 to anything is always going to be 1, right? And they're also going to pass through 0, 0 as long as you have a positive power. Again, I'm not going to make you graph them. But here are your positive constant of variations. Here are your negative constant of variations. And I hope that it's obvious why they're the exact same image, just one's above the x-axis and one's below. Because making it negative is just a reflection of the x-axis, which we talked about in 1.6. So it's the same stuff. It's just been reflected down below. Okay, so what are our 4 shapes? Our 4 shapes are going to be this one, which just looks like the reciprocal function. If you remember that from your 12 basic functions, that's if a is a negative power. Because what you're going to end up with is like over x to some power. So you will end up with a reciprocal shape. If a is exactly 1, well, then it's just linear. It's just kx. And that's why you get these straight line here. If a is bigger than 1, then you get something that's parabolic or cubic or anything in between, like a 2.5, 3.1. They're all going to do that. But then tricky one is this one, at least in my mind, that's the tricky one. That's if you're dealing with a fractional power between 0 and 1. Then you're going to get things like the 1/2 power, the 1/3 power, the 1/4 power, root types. And that's why they look like, kind of like a square root graph. Those are your 4 basic shapes. And then, like I said, these 4 are the exact same thing, just reflected over the x-axis. Power function formulas with positive powers are statements of direct variation, and power formulas with negative powers are statements of inverse variation. And that's actually what we're going to focus on, inverse and direct variation problems. So we'll start with one modeling question so you can see what we're talking about. And then we will scribble out what's actually in the notes and write in the 2 examples I want you to be able to do, and we'll go from there. From empirical evidence and the laws of physics, it has been found that the period of time t for the full swing of a pendulum varies, and when we say varies, we mean varies directly, varies as the square root of the pendulum's length, provided that the swing is small relative to the length of the pendulum. Express this relationship as a power function. So we're not even solving for anything, we're just writing the model that we would use. All right. So what we need to do is we need to probably define some variables. Oh, I forgot to grab my pens. So we said we're going to define our variables. Okay. We were already told that time is capital T, and we know that we're talking about L is length, so we need a function for capital T in terms of lowercase l. Purple is a good color. So we know that the time with respect to the length is, so this is T of L, capital T of L. Now, it didn't tell us what our constant of variation is, which is our K. So we're just going to say K. But it does say that it varies directly. What that means is it's K times our variable with some power instead of K divided by our variable with some power. And see, that's the difference. For direct variation up here, you're going to get KXA, KX to the A. Whereas inverse variation, you're going to get K over X to the A. That's the difference. So if it says varies directly or it says varies as, then you just put that K right in front of your X to the A. Ours says it varies as, which means varies directly as, the square root of the length. Now, while this is a power function, it's not written in power function format. Power function format is K times X to some power. So we're not going to use X. Obviously, we're going to use lowercase l. So we're going to say K times L to the what power? 1/2. There it is. So the time for the pendulum swing with respect to its length is K times L to the 1/2 power. That's it. That's how you would set up that formula. So that's technically modeling using this information. We're going to do one example of direct variation and one example of inverse variation, and we're going to call it a day with this material. Cool? All right. So what's in your notes? You can scribble that junk out and write this question in, just like I did. So we're going to do this first example of direct variation. It says y, don't worry, I'm not going to start working. I know you guys are writing. Y varies directly as the square of x. The one we just did was the square root. This is the square of x. So what we're going to do here is we're going to say, all right, if we set up the formula the way we just did in the last question, and then use given values, can we find unknown values? And really that's it. And that's the only example on your test from this material. I can't remember if it's a direct or an inverse, and I wouldn't tell you anyway, even if I did remember. But the point is, there's only one. So we'll just practice the one skill that is really important from this material. Y varies directly as the square of x. If y is 45 when x is 6, what does x equal when y is 80? No, don't guess. There's no guessing. I was trying to figure out what color I wanted to write in. I like green. So it says varies directly. Because it says varies directly, that means we're going to be working with y equals kx to the a. Because it says varies directly, that k sits right in front of x to the a. And we know what a equals. It says it's the square of x. So it's a 2. A is 2 because it's the square of x. So y equals kx squared. We have a matching xy pair. So we can use that information. We can substitute that x and that y in, solve for k. And then once we have solved for k, We could then sub in y equals 80 to figure out what this unknown x is. Y is 45, x is 6. So 45 equals k, and I'll do like this, where x is 6. Boom. Okay. 6 squared is 36. So I have 45 equals 36k, and then we're just going to divide both sides by 36. K equals 45 over 36, which reduces. 9 goes into both of those. Gives me 5 over 4. There. Now we know what k equals. Now that we know what k equals and we know what a equals, we can plug in anything we want to solve for anything else that we want. Switch over to blue. I like blue. Y equals 5/4 x squared. A good old quadratic. We'll plug in y equals 80 and solve for x. Ta-da! Not bad, right? This isn't scary, is it? I'll use 80 for substituting in again. 80 red, excuse me, for substituting in again. I want that 5/4 to go away. What should I do? Multiply by 4 over 5. That'll do it. Let's multiply both sides by 4/5. Reciprocals cancel each other. And if you divide before you multiply, life is pretty easy. 1/5 of 80 is 16, and 16 times 4 is 64. Now we just solve for x. Take the square root of both sides. What are we going to get? Now here's my question. Is there a plus or minus?
Yeah.
Damien's just going to take both sides of the argument and hope that one of them's right. What do you guys think? Plus or minus or no?
Yes, because when you square it, you got it. No, because no. Up and yes.
Oh, but x can't be negative in this any points.
These are power functions. So x cannot be negative. It's not a standard quadratic. Because it's talking about variation, this is a power function. We cannot use negative x's. Therefore, x will only be positive 8. Normally there would have been a plus or minus there. Yes, I agree. But because we're talking about a type of variation, we know we're working with a power function, which means we have restricted our domain to 0 and bigger. All right. Next example / last example, inverse variation. So once again, scribble out what I have there, and we're going to write in this question. So we have that y varies inversely as the 4th root of x. Well, since it says inversely, this means k over x to the a. Because it says inversely, we're talking k over x to the a. Y equals k over x to the a. That is inverse variation. And it specifically says the 4th root. So what would a be then? 1/4, because it's the 4th root. There we go. Sorry, I was writing a. There we go. X to the 1/4 power. That is the 4th root. Ta-da. We have a value for y, and we have a value for x. We're going to use that information to figure out what k is. And hopefully I have enough space to pull this off. We know that y is negative 4. We don't know k, but we do know that x is going to be 81. So what is the fourth root of 81? Remember, we can't have negatives because the power functions. Technically, usually we would, if we were trying to solve, yes, we would say plus or minus. But because we're talking power functions here, we're just going to have to say 3. He's not wrong. Just we have to be careful because it's power functions. So you just multiply both sides by 3, and you will get that k equals negative 12. And now that we know what k equals, we can write our power function correctly and plug in x equals 16 to figure out what y is. What have I not written in yet? Purple. I haven't written in purple yet. Y equals negative 12 over x to the 1/4. And all we have to do is substitute in x equals 16. What is the fourth root of 16? It is 2. So what we have here is that y equals negative 12 divided by 2, which is negative 6. And we're finished. That is the only skill set that I need you to have for the chapter test from this material.
Which one?
I-
Inverse or direct?
You need to have both for the test, inverse and direct. But hopefully it's easy.